So we will start with a paper, Automated Planning for Linear Shipping Fleet Repositioning by, well, many people, but Kevin is going to give the presentation. That's great.
Thank you. Yeah, this is a paper with a lot of co-authors, Amanda and Andrew Coles at King's College London, Christian Kroer, Adam Britt, two master's students at IT University of Copenhagen, and my advisor, Rune Møller Jensen. And also, I'd like to thank Mikkel Mødov Siggaard and Sean Long, who helped us with data gathering and problem specification at Maersk Line, our industrial collaborator. So, what's the motivation for this problem? Globally, there's about 100 repositionings monthly, and I'll get into what a repositioning is in a second. The cost is from $200,000 to $1 million per vessel, and a vessel is one of these, a big ship carrying lots of containers. Maersk Line estimates they saved $100 million last year repositioning by hand. So you can imagine what we could maybe do with automated techniques. The outline for my talk today: first, I'm going to go over what the problem is. What is this problem of fleet repositioning? Then I'll talk about the PDDL domain that models this and discuss three solution methods. First, linear temporal optimization planning, a novel method combining partial order planning and linear programming. Then some modifications to the POPF planner in order to handle this domain and solve it efficiently. And then a mixed integer program that also models the domain in sort of an OR approach. Finally, I'll give you some computational results and conclude. So what are linear shipping services? Well, it's sort of like a bus route. Essentially, linear shipping is it consists of cyclical routes that call ports on a weekly schedule. And this schedule is very important to linear shipping. It's what separates linear shipping from other forms of maritime transportation. And following this schedule is one of the critical components of any optimization in the linear shipping domain. So services consist of multiple slots. And each slot has one vessel in it. So the AC3, for example, would have maybe 5 or 6 slots. And in each of these slots you have a vessel, and say it starts at Yokohama on a Sunday, and then it starts sailing. And on the next Sunday, that vessel would be maybe in Xiamen, China. And you'd also have a vessel at Yokohama again sailing around. So you have this regularity every week, a vessel in each port. Then what is repositioning? When the economy changes and production shifts between different countries, liner shipping networks have to be updated. If a liner shipper doesn't update their networks, they're going to go out of business. So we did a case study with Maersk Line where they were creating a new service called the Intra-WIXA, that stands for West Coast South America. And this new service needed 3 vessels. However, those vessels aren't in South America. There's very rarely extra vessels available over here. They were all in Asia. One of them was on the CHX service. And so we need to move those vessels from the services they're on to this new service in a cost-efficient manner. In fact, we want to find the optimal cost solution for moving those vessels. One way to do that would be to simply just naively sail across the ocean. I mean, that's one option, just sail. The problem is that that's really expensive. So let's look at some options for making this process cheaper. The first option is a sail-on service. So let's look at the AC3 service, for example. We could take a vessel from the CHX service, sail it over to the AC3, and then join the AC3 service, essentially removing the vessel already in the AC3. We'll just ignore it in our optimization now. It doesn't matter anymore. And we'll sail instead on the AC3, bringing the cargo along the service across, say, to Balboa, and then we can join the Intra-WIXA. This is much cheaper than having one vessel sailing here and one vessel sailing here. Now we're sailing one vessel across, and even better, we don't have to perform the backhaul. On a lot of liner shipping services, the backhaul is an empty sailing because of trade imbalances. There's almost no cargo going here, so we don't have to do it anymore. That saves a lot of money. Another option is to sail with equipment, and by equipment, I mean empty containers. So in Dalian, they manufacture refrigerated containers. There's a lot of extra containers there, but there's no fruit in Dalian. The fruit is over here, and they need refrigerated containers to send it to the markets across the world. So we can take a vessel, sail it up here, grab some empty containers, and bring them over to South America. And that's essentially lowering the costs for the network, because otherwise Maersk Line would have to maybe hire a ship or sort of bump customer cargo to move those containers. Another option is slow steaming. So if we look at these vessels can sail at different speeds. They have a maximum and minimum speed that they can sail at. So we look at the cost of sailing. If you sail fast from Yokohama to Los Angeles, up there somewhere, it would cost about $900,000 if you sailed in about a week and a half, very fast. However, if you sail slowly, it takes 2.5 weeks or so, $485,000. That's a huge savings of money just by going slowly. So we want to try to find plans for sort of optimal plans where we can slow steam our vessels and still make our time deadlines. Finally, we're going to respect cargo flows. I don't take an explicit view of cargo flows in this model, but we use actions that don't significantly disrupt the cargo flows in the network. So what are the difficult components of this problem? Well, first are the vessel interactions in the sail on service and the phase-in. That's when you join a service. Basically because the sail on service is essentially a free way to move between two ports. So you want to try to find the cheapest way for vessels to use a sail on service. And so they're all going to kind of compete to use this. Then in the phase-in, we want to have this sequential week phase-in, right? If you imagine when you're waiting for a bus, if two buses come at the same time, that's basically useless, right? You want to have a bus coming regularly. It's the same with liner shipping. So we need to make sure that that our ships are phasing into the service in a regular fashion. Action duration linked costs. I showed you this graph just before of a sailing action. So we want to try to model these continuous costs rather than discretize these sailing actions because we want to know about basically what hour a vessel arrives at a port. And if we have to discretize that action, we'll end up with 200 or 300 actions in order just to sail one route. And finally, the hotel cost. This is a fixed hourly cost of the vessel that we incur from the point where we leave a service until we join the service again. This fixed hourly cost involves kind of complex modeling. We have to use something called an envelope action in PDDL, and I'll show you how to model that in linear temporal optimization planning in a second. Let's take a look at the PDDL 2.1 domain. We have several high-level actions. The phase-out, this is when you leave a service. This is a phase-in, that's when a vessel joins a service. Sail, so that's just moving between two ports at some cost. Sail on service, that's when you move between several ports doing the sail on service opportunity at extremely low cost. And sail equipment, that's also sort of moving between two ports but with a different cost structure than the sail on service. So there's a few interesting aspects of this model that a lot of PDDL domains don't have. The first is the number of timed initial literals, TILs. Our instance with the lowest number of TILs has 146. This is higher than most domains have even in their largest instances. And our biggest one has 266. So why do we have all these? It's the liner shipping nature of the problem. Say, for example, vessel may phase out, vessel 0 at tangent helipus at 16, and then at 16.1 we get rid of it already again because we want the vessel to phase out at a specific time so that we can incur the hotel cost if the vessel's waiting around. So the hotel cost envelope actions look kind of like this. This is a picture from our technical report which kind of accompanies the PDDL domain. If you phase out a vessel and then phase it in, and you have a sail action that can't take the entire time, you have all this waiting time, and so the hotel cost action encompasses that entire period and takes all the costs into account. Then we have these strange actions with costs at decline with duration, and finally we have the required concurrency in our model as well. Let's take a quick look at some related work and kind of say, well, okay, why can't we model this problem in these planners? SAPA LPG and that benefit planners can't model duration-dependent effects, and we want to have the sail action modeled correctly. Kong-Ming doesn't allow multiple updates to a single variable. We have multiple ships and some interacting actions. And TML PSET doesn't optimize plan metric. Our goal is cost optimization here, not mixed-band minimization. Okay, so now we've seen the problem, PDL domain. Let's look at solution methods. First, I'll talk about this novel method, linear temporal optimization planning, LTOP, and go into POP-F in a minute. What is LTOP? So LTOP is a partial order planner. So we look at a normal sail action using a state variable representation. You have your preconditions and effects, sailing from one place to another. Very simple. What we're going to do is we're going to attach an optimization model to that action. So kind of merge the whole thing. And now I have a minimization of some linear objective term, as well as constraints over some optimization variables in a single action. And what this gives me is the ability to to calculate lower bounds on action costs and to merge sort of actions in their optimization models and solve this problem to optimality. So let's look at an LTOP plan. Imagine these are our some conditions we want to have in our goal state, and this is what we get in our initial state. And we're just going to solve this by partial order planning. So I add some action with a causal link. Notice that the optimization model comes with it. This action has a specific optimization model associated with it. So then I can add another action to the plan. Now I have two optimization models in my partial plan. What I can do is I can merge these two optimization models, throw them into a linear programming solver, and get a lower bound on the cost of the plan. The reason I can get a lower bound is that we have the requirement that the action cost stays positive underneath its constraints. That means even if I add another action later, I know the cost can only go up. We also use a modification of the Hmax heuristic in order to compute a lower bound on the cost of actions not yet in the plan, so we can get some kind of good pruning for our later branching bound I'll show you in a second. So if we keep going with this plan, maybe I have an action that deletes this red fact here, that is a threat, and then I add an ordering constraint. Our ordering constraints are also handled by the linear program, because each action has a start and an end optimization variable, so all we have to do is simply order those variables in the LP. So then I have a complete plan. What can I do with this? I can merge all the optimization models, and I get this one big optimization model, but it's still just an LP, so I throw it in the Cplex, solve it, and now I know the optimal cost of that complete plan. I can use that as an upper bound in my search, or maybe I'm done and I can return the cost to the user. Quick look at the branch and bound. So we start with an empty plan, and maybe we have some lower bound of 500. We know it at least costs that much. And then I branch, and maybe I have a complete plan. So now I can solve the LP, and I get an upper bound of 600. I know my cost is between 500 and 600. I keep branching, and then I get a lower bound of 650. Okay, I prune that. I can also prune for temporal inconsistency. If the LP says, the problem's infeasible or unbounded, I can just prune that branch. And then the branch and bound continues. Very simple. So that was LTOP. Now let's take a quick look at what's different in POPF from previous conferences. So it's a forward-chaining partial order planner, but it's a satisficing planner. So it's very important the LTOP is a complete optimal planner, whereas POPF is basically satisficing except with some admissible heuristics. And we've modified two things. So we have TIL handling changed. It's modeled in a MIP now with a disjunctive temporal program. And we also have some cost estimation action pruning in POPF, but that's sort of like the branch and bound, so I'm going to skip that. Let's look at the TIL handling. So what does POPF do? It adds dummy actions for the TILs. So take, for example, we have a dummy action that adds a fact P, and maybe we need that fact in order to do a phase out. So this fact would be immediately deleted, but phase outs, there could be multiple phase outs for a vessel at a single port over time. So this fact kind of comes in and out, and that means with these dummy actions, we now have a choice. Do we put the phase out here or here? And you imagine if this continues, you have a lot of different places where you can put this phase out action. That creates a lot of different sort of branches that you have to explore, a lot of places you have to search. So we leave the choice of which window to use to a MIP. And we can't just use some disjunctive temporal program solver because of the continuous costs in our problem. So what do? Let's say you have a fact that is added and deleted periodically by TILs. In the first case, if no action adds or deletes F, we can add the following constraints where step I is a continuous variable telling us what layer of the plan we should use this fact in. This is where the fact becomes true. This is where the fact becomes false. These are coefficients. WIK is a binary variable indicating essentially whether we're using that window with that fact. And then we just have a mutual exclusion constraint so that we only accept one window for the fact. You don't want to use multiple. Then we have a second case where no action adds F. Actions with a precondition on F delete F. So we're going to add these constraints again, but we're also going to add this constraint where capital F is all the layers of the plan that refer to fact F. And we're just going to constrain those to be at most one of those layers. Okay, that was our small modifications to POPF. I'll get into a few more of them later in the results. Now let's look at our mixed integer program really quickly. I'm not going to go over the whole thing. There's the model's in the paper if you want to read it. It's basically modeled with an activity graph, sort of a flow problem formalization. And on the one side of the graph, you have the phase-out actions. That's when you're leaving a service. And on the other side, you have the phase-in actions. This is when you're joining the service. This is essentially the goal state. And in between, you have some various activities you can perform. So what are variables? We have, do we use an edge in this graph? Is an action used? This W is an auxiliary variable in the model. And then for each of these actions, I just have a start and end time, sort of similar to LTOP. And then I also have variables representing the hotel time start and end. And this model involves a graph for each vessel with some mutual exclusion constraints between the graphs in order to prevent multiple vessels from using a single action. For example, multiple vessels can't do a single sail on service. That's not allowed. So we have some, and we also have some extra constraints, some side constraints to handle the phase-in. But overall, it's a fairly standard flow graph formulation. Okay, now let's take a look at the computational results and then conclude. So we made a benchmark of 10 instances based on a single real case study from Maersk Line. There are sort of variations of the problem so we could see how the problem scales. And we use a mixed integer program on these small instances, and it solves rather quickly. The mixed integer program is faster than LTOP. We configure LTOP with several different heuristics. D stands for domain-specific heuristics. So what we do is, for example, we prevent multiple sail actions one after the other because we can basically use a triangle inequality. If you go from A to B to C, then just go from A to C. And we also have a way of optimally completing plans when a vessel uses a sail on service action. Because of the way some pieces of the plan are fixed in time, we can simply complete the plan really quickly and don't have to have extra branching. L stands for the LP heuristic, and H is Hmax. So we did some various combinations. Generally, this column's the best. The domain-specific heuristics are rather helpful, and the combination of the LP and Hmax are a rather strong way of estimating the cost of plans. And also PopF is configured with admissible heuristics over here. Remember that PopF wasn't really designed for this, so it's not really that fair a comparison. We also have a forwards and reverse PDL domain. So when we look at all the instances, however, once they start getting a bit bigger, the LTOP configured with domain-specific heuristics, the LP and Hmax, starts to outperform the mixed integer program. They do scale together, but LTOP is a bit faster on all the instances with various configurations, with various equipment, cabotage restrictions, which are sort of laws for handling where ships can go, number of ships, number of sail on service opportunities. PopF unfortunately times out on these in the optimal case. We give a timeout of 1 hour, but we'll see that PopF does a bit better in the case where we do satisficing. And so in this column, in the parentheses, we have the optimality gap of PopF against the optimal plan found by the MIP and LTOP. And in here, it's the CPU time to find that plan. So we try to make span minimization just to show that on this problem, make span minimization is a really bad idea. Because if you do a make span minimization, remember that all the ships will basically be sailing at top speed, so they're going to be using a lot of fuel. When, on this instance, for example, make span minimization solves very quickly. It only takes 10 seconds. But we get an optimality gap of 15 times worse than the optimal solution. So it's unacceptable to our industrial partner to have solutions like that. In our standard column for PopF, we're using these new TIL abstraction techniques, as well as doing something else with the MIP. We don't actually solve the MIP to optimality in every step. We only have to solve the MIP in the goal states. Otherwise, we just solve the LP relaxation, because that's much faster. Solving a MIP at every step is just too slow. And just to show that this TIL abstraction technique actually works, when we turn it off, the optimality gap increases by quite a bit. The solutions simply aren't as good. And also, okay, now looking at all the results, when we don't use this MIP relaxation technique, the results are also not quite as good. I mean, their answers are found fairly quickly. However, the optimality gap is often rather high. And then finally, we used a reverse domain because we thought, well, LTOP works in reverse and worked fairly well. Maybe because PopF is using a forward domain, the performance isn't as good. Oddly enough, though, the reverse domain actually didn't really give us much improvement. It's actually worse than the forward domain in PopF. So to conclude, we're kind of left with a question, what is this problem? Should this fleet repositioning problem be modeled with a MIP, automated planning? It kind of goes on the border between planning and operations research techniques because the graph in the MIP isn't actually all that big. You can model it in a MIP pretty reasonably, but at the same time, planning gives you much better modeling tools than the MIP does. If I have to add a new action, it's much easier in the PDDL model or even in LTOP to add that action in resolve than it is in the MIP where I have to go play with some binary variables and add some extra side constraints. So the future work is kind of investigating what features of the problem make this problem better for planning, better for MIP, as well as adding container flows and revenues to the LSFRP. I actually have a new model doing those already, which once I add this sort of multi-commodity flow of cargo, the MIP starts to become much better than the planning techniques. And we have this PDDL domain available for you to download and play with if you'd like, both the forwards and reverse domains. It's available at decisionoptimizationlab.dk/datasets, and I hope you'll download it and try it out. Thank you.
Nice to see a direct comparison between MIP and planning on a problem like this. I think that's incredibly useful. Can you just say a bit more about whether this is a problem that scales up? I mean, can you make very large instances, and how does MIP scale as the instances get very big? Or, I know you just said that if you add additional elements to the problem, then MIP outperforms planning, but it'd be very nice to understand a little bit better what that trade-off is.
Yeah, that's a really good point because we're only working with an instance with 3 vessels there, and I now have data from Maersk Line with instances up to 14 vessels, so I'll be doing the same comparison with those and trying to see what the results look like. I think 14 vessels is actually going to be just about the max. You don't see liner shipping services much longer than that, so that's probably as large as this problem really goes.
And do you have a feeling for where the bottleneck for MIP would be? I mean, is it going to be that dimension that breaks it, or is there some other thing, or is it going to get better than planning, or what?
I think that is the main dimension because the hotel cost is really hard to model in a MIP. There's a lot of things you can kind of change in a MIP and get the flow problem maybe to be a bit faster or whatever, but the hotel cost for each vessel is a real pain. Because you're stuck with big M constraints no matter what. There's nothing you can do about them because you have to set a variable based on where this vessel sort of phases out, and there's really no good way of embedding that cost into the graph because of the sort of the flexibility of a lot of the actions because of the scheduling problem. So I think, yeah, as you get more vessels, it just becomes way harder for the MIP.
Right. Thanks.
One more question.
So you mentioned that you had required concurrency in the problem. So I'm just wondering, do you actually have required concurrency, or is it because of that's the only way you can encode the hotel cost and time windows and things like this?
Yeah, I mean, I think that's the only way I can encode the hotel costs in PDDL.
Yeah,
in LTOP, I don't need envelope actions, which is kind of nice. I can use these optimization variables in there. So I suppose it's maybe I don't actually need it if you use a different modeling format.
Well, or if there was another.
If there was another. I mean, LTOP doesn't accept PDDL. It doesn't. I just wrote this planner myself. It's not like some advanced planner or anything.
So you mentioned something right at the end about the modeling time that it takes in order to model the PDDL against modeling it in as a MIP task. So what in the order of what you are talking? Is it about 1 day more, or is it a week, or so how would you evaluate the time?
I think that's the challenge with MIPS because it really depends what you're adding. For example, say I want to have the vessel support being repaired at some point. These vessels have to be repaired every 4 years, and you might want to do that during a repositioning. I could just add an action to the PDDL model, repair. Very simple. It would be a derivative action of about a week. It would essentially have no cost, and it would be required by the goal state. I could probably add that in 10 minutes. If I wanted to do it in the MIP, I now have to change the way the graph is formulated. It's essentially embedding the preconditions and effects of that action into the graph. Coding that's going to take probably the whole day just to work out the bugs.
Okay. And so what is the status now with respect to the company? Are they already buying your stuff, or?
No, not yet. We are trying to do a more close kind of prototype collaboration and see sort of how our results stack up. That's the next step, is really comparing our results against what they've done, and trying to get this research more into practicality.
Okay, thank you. So while the next speaker goes and prepares herself, is there someone from, so Steve, are you giving the talk? At some point you will have to come here and then give me the slides and so on. So next paper is CP and MIP methods for ship scheduling with time-varying draft, and it will be presented by Elena Kilareva, and it's joint work with P. Kilby, Sylvie Thibault, M. Wallace, and S. Brandt. That's what I have. I don't have the name, sorry.
Hi everyone, my name is Elena Kilareva, and I'll be telling you about ship scheduling with time-varying draft. What's this doing?
It's very busy right now.
Yeah.
It shouldn't be doing anything else. Different computer. Did you press that button?
No, I pressed. Sorry about that. So I'll start with just introducing the problem. The specific problem I'm looking at is maximizing cargo throughput at a bulk export port. And I'll tell you a bit about why draft restrictions are important for this problem. Then I'll talk about how we model the problem using both constraint programming and mixed integer programming. And finally, I'll talk a bit about some improvements to the CP model that we tried. So ship scheduling in general is about choosing sailing times and amounts of cargo so as to maximize the profit or minimize the cost of transporting that cargo. And it needs to obey any safety rules in effect at ports. Now, one common safety rule is restrictions on draft. Draft is the distance between the waterline and the bottom of the ship's keel. So as you load more cargo onto a ship, the draft increases. And if you load too much cargo on, then there may not be enough water for the ship as it's leaving the port. So the ship could be at risk of running aground. So for this reason, most ports have safety restrictions on the maximum draft. Now, existing approaches to ship scheduling either don't consider draft at all, or they just have constant draft restrictions. So for example, ships can only enter a port if their draft is below 13 metres, and they can never enter a port if their draft is above 13 metres. But in practice, most ports have draft restrictions that vary with time. Because if you think about it, at high tide, there's more water available for the ship to sail. So you can load more cargo on safely. So the reason why we want to model these time-varying draft restrictions is this gives us more accuracy in our draft constraints. So this lets us take advantage of being able to load more cargo on at high tide, or when the waves are low, or when the current is not very fast. And there at the bottom is an example of a typical draft constraint. So as you can see, it's fairly complex and it depends on a lot of different factors: tide, wave, current, etc. So this is not just a simple function. The exact problem I'm looking at is quite different from Kevin's problem. So I'm looking at maximizing the cargo throughput at a single bulk export port. So I'm looking at bulk cargo as opposed to container cargo. Bulk cargo means things like coal, iron ore, wheat, things that are carried directly in the hold of a ship rather than in containers. So we're looking at a real port, Port Hedland in Western Australia. This is Australia's largest iron ore export port. And because this is an export port, the outbound ships are usually full and the inbound ships are empty. So this means that the outbound ships have much larger draft and they need to sail at high tide. But inbound ships can sail anytime. Also, at Port Hedland we have a narrow channel, so ships can only sail through it one at a time. Now this means we have sequence-dependent separation times between ships. So for example, if we have two ships sailing out of the channel, the ship closer to the exit, if the ship closer to the exit sails first, the other ship may be able to sail straight away without having to wait. But if they sail in the opposite order, then the ship closer to the exit has to wait for the other ship to pass before it can start sailing. So the separation time between pairs of ships depends on the order in which those ships sail. And the objective for this problem is to maximize the total cargo carried on this set of ships, because the amount of cargo carried depends on at what time of the tide the ship sails. And there on the right is just a picture from the control tower at Port Hedland. So you can see a couple of ships in the background. So we actually have, our model has been implemented in a commercial system, which we demoed on Wednesday. So the way that works is you select the high tide that you want to schedule ships for. You select several ships you want to schedule. For each ship you need to enter several input parameters, as shown here. And then the system prints out a result. So the x-axis here indicates the time at which the ship sails. The blue curve in the background is the height of the tide plus the depth of the water. And the height of each bar is the draft that each ship sails with. So some features of this problem that make it a complex problem to solve. First of all, we're trying to solve it to optimality, because these are really huge ships, so even 1 centimetre of extra draft means you can load 130 tonnes more iron ore onto an average Cape-size bulk carrier. So even a small reduction in quality of the schedule means that we carry quite a bit less cargo. So we really want to find the optimal schedule. The second reason why this is a complex problem is that it's oversubscribed at the high tide. So in general, the problem is undersubscribed. There's usually enough time to be able to sail all the ships. But all the ships want to sail close to the peak of the high tide so they can carry the most cargo. So around the peak of the high tide, the problem is very tightly constrained. The third reason why this problem is complex to solve is we're using a time index formulation. Because the draft changes over time quite quickly, we need to model it with these just by specifying the draft at 5-minute increments. Because it depends on tide, waves, etc., it's not possible to specify just with a simple function. And the fourth reason why it's a complex problem is that the constraints are very sequence dependent. As I mentioned before, the separation times between ships are sequence dependent, but the constraints on availability of tugs, which are the small boats that are used to help the ship enter and leave the port, these are even more sequence dependent and even more complex. And I'll talk about those in a few minutes. So the basic CP model without tug constraints is fairly simple. We have some constraints on the earliest time with which a ship can sail. That's the earliest time that it's ready, loaded and ready to go. We have some constraints that specify that if we have incoming ships, the berths that the ship is going to must be empty before the ship arrives. Then we have constraints on separation time between ships to make sure that if something goes wrong with the ship in front, the ship behind has enough time to stop so they don't run into each other. And the objective function that we're optimizing here is maximizing the total cargo for this set of ships. So that's the draft multiplied by the tonnage per centimetre of draft for all the ships that are included in the schedule. So this basic model without the tug constraints, we compared it against existing approaches, such as constant draft without time variation, and a manual scheduling heuristic that's used in practice by schedulers at Port Hedland. So this is a really simple example with just 3 ships and the separation time just being half an hour between each pair of ships. No sequence dependence. But even for this simple example, we find that constant draft and manual scheduling don't find the optimal schedule. So with constant draft, because we have to have just one draft limit that has windows wide enough for all 3 ships, it means we have to have a draft limit of 18 metres here. So that means that ship A, even though it could sail with 18.1 metres, it ends up being scheduled at 18 metres, so 10 centimetres less. And the manual scheduling approach that's used in Port Hedland is they order the ships from largest to smallest, or order them by weighting in the objective function. So in this case, that would be by tonnage per centimetre of draft. And they schedule, first of all, the largest ship at the earliest time it can sail, then the next largest at the earliest time it can sail, and so on. So that approach, ship A gets scheduled at the earliest time it can sail because that's the biggest. Then that blocks out the start of the window for ship B, so ship B gets scheduled after ship A. And then ship B blocks out the 18-metre window for ship C, so ship C gets scheduled with 10 centimetres less. So in both of these really simple examples, you end up with 1,300 tonnes less cargo being carried on this set of ships. So that's $200,000 less iron ore. And we looked at some larger problems in the paper, and on average we found that the optimal schedule had 120 centimetres more draft per set of ships than the constant draft schedule, and 15.8 centimetres more draft than the schedule produced by this manual scheduling heuristic. So we're currently in the process also of comparing against real schedules produced by the Port Hedland schedulers, but it does look like the optimal schedule can allow more cargo to be carried on the same set of ships, thus reducing shipping costs. So that very basic CP model that I showed you before, that was the one that we put in the first version of the prototype, which we demonstrated to the schedulers at Port Hedland. And the main feedback that we got was that the schedules were not realistic because they didn't include constraints on tugs. Tugs are these small boats that you see there that are used to help ships enter and leave the port. So in our improved model, we needed to include these tug constraints. But when we tried to implement them, it turned out the tug constraints scale really, really badly. Because the duration of time that a tug is busy depends both on the first ship it works on and on the ship it's going to work on next. So if a tug works on an outbound ship and then switches to an inbound ship, the duration of time that it's busy is only as long as it takes the outbound ship to leave. But if it works on an outbound ship and then has to go to another outbound ship, then it has to first travel all the way back into port. So it's busy for a longer period of time. So the first approach we tried for modelling the tug constraints was just allocating tugs to ships. But this was really, really slow and it couldn't solve even very small problems. So then instead we tried counting the number of tugs that were busy at each point in time. So this was a bit faster than allocating tugs, but the turnaround time, the time that each tug is busy, is still sequence dependent, so we still had to keep track of the origins and destinations for each tug. So this was still too slow. So the approach that actually worked was based on 2 key assumptions. First of all, at Port Hedland we have a narrow channel, so ships can't pass each other in the channel. We can only have one ship sailing through at a time. And secondly, at Port Hedland the berths are close together compared to the length of the channel. So this means that the travel time for a tug from the berth out to sea, or vice versa, can be considered independent of berth location. Now this second assumption in particular is not going to apply to every port, but just from a quick look at the maps of about 10 ports, it looks like it should apply in about 9 of those cases. So we think it's going to apply in the majority of ports, but there probably will be somewhere it doesn't apply. So for those ports we will need to extend our tug model. But if these two assumptions apply, then that means that incoming and outgoing tugs can be tracked separately. So this allows us to split a sequence of ships into 4 different scenarios. And in each scenario, we can model the tug constraints separately and that they don't affect each other. So we either have a set of outgoing ships one after the other, or a set of incoming ships, or we have an outgoing ship followed by an incoming, or vice versa. So the tug model is quite complex. I'm not going to go into all the details of that, but it's explained in more detail in the paper. But as you can see, even with these 4 scenarios, it's a lot more complex than just the basic CP model I showed you earlier. We also model this problem as a mixed integer programming model, which is, the model is quite similar to the CP one, just all the constraints linearized. And again, it's explained in more detail in the paper. So we implemented both models in Minizinc and solved the CP model using the G12 finite domain solver and the MIP model using the OSI CBC solver. And we tested them using problems of varying number of ships and varying levels of constrainedness. So the problem sizes range from 4 ships to 10 ships, and they sound like quite small problems, but they are actually realistic. So at Port Hedland, the record for the maximum number of draft limited ships sailing on a single tide has been 5. They want to move up to about 9 ships over the next 5 years. So these are realistic size problems. The different problem types that were modelled included either all ships outbound or ships travelling in both directions. And also we looked at problems which were very tightly constrained, had very narrow sailing windows. So problems with all very big ships. Or with wide windows, so a mix of bigger ships and smaller ships. And with a 5-minute cut-off time for the calculation. We looked at some search strategies for the CP model, and these are described in this paper. And for the MIP model, we'll let the solver choose the strategy. So the results show that the CP model is much faster than the MIP in all cases. But it's possible that maybe the MIP may be able to do better with other solvers, other search strategies, or a better model. We also looked at a few improvements to the CP model. So we tried adding sequence variables specifying the ordering between pairs of ships and searching on the sequence variables first. We tried converting multidimensional arrays to 1D arrays because these are more efficiently implemented in the G12 FD solver. And we tried sorting ships and assigning times to the biggest ships first. So the results were the sequence variables on their own were actually slower. But as you'll see on the next slide, when combined with the 1D arrays, they become faster than searching on draft or time directly. And the 1D arrays produce the biggest effect. So that's not any kind of really fundamental result, but it's something that maybe could be automated in a future update of Minizinc. And it's something that may be worth considering when you're modelling a CP problem. Because if you're using a